I hope I'm audible. Maybe someone can confirm in the chat once. Uh, yeah, thank you. Yeah. So good evening, everyone. My name is Aveen Dayal. I'm a PhD scholar at IIT Hyderabad, and I'll be conducting these live sessions in the Monday slot from 7 to 9 p.m. for the course Deep Learning for Computer Vision, taught by Professor Vineet. And like every week, we conduct these live sessions to discuss some example problems and some code walkthroughs, which will help you solve your assignments, and also some other different perspectives about the contents that the recorded lectures which are conducted. Sorry, regarding the contents which are uploaded by Sir, right, in the recorded lectures. So, and we also have other live sessions happening in the week, which will be on Tuesdays and Saturdays. So in this week, we'll be talking about the contents related to explaining how CNNs work. That is about visualizing the bottleneck features and also about the CAM activation maps and a little bit about those topics, basically last week topics. So I'll just share my screen and we can get started with this week. So, this week we'll be talking about, like I said, explaining how the CNN model works. And like every session, if you have any queries or any questions, you can either post it in the chat or you can just raise your hands and I'll ask you to unmute. So, just to make the session more clear, like I want everyone to be on mute, and if you want to unmute, you can always raise your hand. So, yeah. So coming to the visualization methods, like first thing is we talked about in the previous week before talking about how CNNs can be explained. In the week before that, we talked about how to create a CNN model, and we talked about how it is used to for many computer vision tasks like classification, object detection, image segmentation, tracking, and everything. You'll learn more about how to do this in the next week sessions, the object detection and segmentation. But all of them have a base model as CNNs, and we know how CNNs work. CNNs, they work because of the operation called as convolution. So you have a filter matrix, you have your input matrix. The filter matrix basically keeps like it's a small matrix which is like 3 by 3 or 4 by 4 or 5 by 5, and you basically keep on traversing that across the input image, and you keep on doing operations across every this patch of 3 by 3, 4 by 4, 5 by 5, and the output will become the input to the next convolution layer. So in this way, what we try to do is we try to learn features, visual features, which are most relevant for doing that particular task. And so that is all well and good, and we said that it works because we also see the accuracies, we also train the models, we see that we get very good accuracies. It also generalizes to test data very well. But in some applications, especially in medical applications or in some other sensitive applications, you just don't need final accuracy, you just don't need the final performance of the model. You also need why the deep learning, or the CNN in this case, is making a decision and saying that this is a particular class. We need that reasoning, because like for example, if you take any biomedical, right? So okay, for if it has to say whether a particular scan is cancer or not, we see ki, okay, it is performing really well, it is performing around 89 or 99% also, but it's maybe it is relating to some other features which are not technically related to cancer. Maybe it's correlating with some other features which might be very spurious correlation. So we want to learn that, we want to make the CNNs learn only those features which are relevant to cancer. So for us to know how to make this relation perfect, we first need to understand what is the CNN looking at. So that's why understanding what CNNs or how CNNs work is very important. There can be many other cases. Medical example is just one case. It can be used like even in defense systems and so many other cases. You need your model to tell you why it is, what is the reasoning it is doing behind selecting a particular output as the final output. So So for that particular reason, people have come up with different techniques, and some of the techniques you can see, like one is the visualization of intermediate layers, and next is back propagating the image. Then we have visualizing data gradient. Then we can also reconstruct the original image in the from the latent space. Then you have some CAMS, deconvolution, and recent methods. So all of these topics, they are very clearly explained in sir's recorded lectures. I won't explain much of in details. Maybe I'll give you some examples for some of these topics, and maybe if you have any questions we can discuss about those. So yeah, so first thing, coming to visualization of intermediate layers. So like I explained, CNN network is the term itself. The deep learning comes if you have a lot of layers in your entire architecture. So we assume, at least in theory, we have a hypothesis that the initial first few layers of our CNN, they extract important features which can be understandable by humans. So what I mean by that, if you look at the features of these, you can see edges, you can see more clearer edges, and for some you can see colors, black and white, or the gradients. So these are all features which can be clearly understood by humans, that okay, this is what this is looking at. Similarly, if you go for another block 2 and block 4 of VGG, if you look at the first block 2, you can still understand. Block 2 is basically the second layer of CNNs. If you look at block 2, you can still see so many features which you can still see as like edges over here, or like some more features which can be comprehensible. But as and more you go deeper and deeper, the understandability of those features, what it is looking at, becomes less and less. Technically it is finding out some patterns, but for as humans to visualize it and see, it is not really understandable for us. So like you can see, there are so many just intensity patches which you can see, not exactly understanding why it is looking at this. Because edges we can still understand, maybe it is trying to find out a pattern of where that object is present in the entire image, so that's why it needs edges. But if you just look at random intensity high and low patches, we can't really say what is happening. But nevertheless, visualizing these intermediate layers of the first few layers, or at least, will give a very good idea of what exactly a CNN model is seeing in that particular image for a particular class. So people have started with this, and it's not always the first few for visualization. Sometimes if you don't want to see exactly where in the image is that CNN looking, but you want to see how far each of the class is from the other class, you can there's something called as bottleneck layer. Bottleneck layer is the last layer after the last pooling layer, the layer which comes after the last pooling layer. We call that vector as the bottleneck layer. And if you use TSNE type of what TSNE visualization method. So TSNE is basically, it projects from any high data, it projects it into a low dimensional data in a very efficient way. So if you use TSNE visualization, you can see how each particular class is forming a cluster, and how the distance between two particular clusters is, and how close all the samples in a particular class are together. And you can see different. So that is for discriminating between classes. But if in each image, each class, you want to see what is the CNN looking at, you can just visualize the first few features and see what exactly is happening. Although this is a good method, because this doesn't need any further retraining of the model itself or anything else. It can simply, after you finish your training, you can just visualize it, and you can see. But it again doesn't offer exact reasoning, because here human intervention is needed. A domain expert needs to look at these images and then see what exactly is the CNN trying to say. There's no automated process. So although this is good, this is not exactly solving the purpose for explainability in CNNs. So then people thought, ki, okay, can we then find an image that actually, maximizes some class score? So what I mean with that, if you say, okay, let's just say I start off with some blank image, 000, everything is zero, and I want to see that at what point that this particular image is getting transformed, right? It will, like, at what pixel values of transformations in these images will make my CNN say that this particular image belongs to class 1 or class 2 or class 3. So so what indirectly we're trying to do is, instead of going in the opposite way like we did in the previous, we try to visualize and see which edges or which features it is seeing. We are saying ki just start off with blank and you keep on doing some random perturbations of that zero image, and at some particular random combination of the pixel values of that zero image will make the CNN say that this is class 1. So then we see ki, okay, what exactly is those non-zero values in that pixel, in that image, input image, is making this particular image classified as that particular class. So this is an iterative process, and in more detail, sir has explained, but this is the basic algorithm. We start off with a zero image as an input. Then we set the gradients of the scores of the vector, whichever class you want. We set the gradients one to be that of particular class, and then we keep on back propagating. And then we do small image update. When I mean by small image update is basically each pixel value you update in a certain direction. Like you, instead of zero, you go it in a plus some value direction, and then you again forward pass that image to the entire network, and you repeat that process. So in this way, you can also actually see what exactly the CNN is looking at. So you can see some of the examples, like we are trying to find the different classes over here. We have like washing machine, computer keyboard, then we have limousine, ostrich, goose, and kit fox. So these all are images. Initially, they were all 0000 images, and then we follow this algorithm. Basically, we do this iterative process, and then we can identify that for washing machines it is basically looking at some rectangles. Like if you can see these versions a little bit like washing machines over here, washing machines over here. Similarly for keyboard, if you can see there are like keys over here which is happening. So some understanding, we people started forming that, okay, if the CNNs are looking for some squares kind of a thing on an image, and then it is classifying as keyboard. Similarly, if you look at limousine, you can see tire marks over here, like sorry, the wheels basically, and you can also see a little bit of window pane of that car. So so we can understand that CNN is not just randomly saying it's a particular class. There is some reasoning happening, although it's not very accurate what we're trying to see, because this is not a great, like this is not the best method to visualize. But yeah, you can obviously see that when you get a similar features in a certain way, it can easily, you don't need the entire detailed input image. You can just send this particular features and it can still say that it is belonging to a particular class. So yeah, I hope this is clear. Any questions, you can always raise your hand, or keep it in the chat. Then after that particular image, after that particular method, people then thought about, okay, why not reconstruct our original image from the latent space. So I think latent space, like everyone knows, maybe I'll just quickly say in one line. Latent space is something, for example, our input image initially will be usually 224 cross 224 or 512 comma 5. So if you want to vectorize that, so this is 224, 224 is a matrix, right? So if uh, can everyone mute yourself? I think Raman, do you have a question, or if there's no question, please mute yourself. Yeah. Uh, Please refrain from unmuting yourself. If you have any questions, then you can raise your hands and then I'll ask you to unmute. Continuing further, sorry. So latent space, I was talking about 224 cross 224 image. And then now this 224, 224, if you want to make a vector, it will become a vector of dimensions 224 into 224. So, and this particular dimension space, like in normally we have 3D space, right? XYZ. Now imagine instead of the three dimension XYZ, imagine a very big dimension space of 224 into 224 dimensions. Now, what people have hypothesized, and I think it's very intuitive also, you don't need all the dimensions in a particular input image to make a guess that what particular class is this image falling into, because there's so much of blank pixels, zero values, right? Most of the times there'll be either zero values or pixel values are not needed to actually, which will not help solving us the task. So then people have tried to come up with different techniques throughout the years on how you can extract relevant features from this particular 224 into 224 space. So, and that extraction is what TSNE also does, visualization. So all of these techniques, inherently what they're trying to do is identify a latent space, which means they'll identify a hidden space where you can efficiently represent your original images, and you don't need any more dimensions other than this to represent your image. So that's why we call that a hidden space or latent space, because we can't observe it. It is something which we try to extract it over the years. In fact, CNNs also does the same thing. So like I said, CNNs have convolution layers. Then after the last pooling layer, we have a bottleneck layer, and then fully connected layers. So that last bottleneck layer is the latent space, because initially we start off with 224 into 224 dimensions, and we keep on reducing. We get to some, usually that bottleneck will be some 1024 or 2048 dimensions, and in that dimension space we try to extract all the important features of that input image. So inherently we can call that as also the latent space. So people then started questioning about, okay, then is it possible, if we have this bottleneck latent space, can we go back and reconstruct our original input? So, and then people used some techniques, like some loss functions and some regularizations of that loss functions, which is basically this first 2 points, the optimization requirements. It should be the images code. It's basically the input image. What it should be, it should be very similar to the given CNN extracted code, which is your latent space. And then we also said ki it should not just be that it is matching some loss function. It should also look natural, like how actual input images look like. It's not just at the end of the day matching each pixel value to each other. It's also how it should look more natural as an image. So based on these 2 points, people have come up with a loss function, like optimization function, which is called phi of x. Basically, this phi of x is your latent space, and phi of 0, which is your original latent space. And we try to basically minimize these two. Uh, we find the subtraction and then the square. Basically, this is the L2 norm. And then we also have some regularization, which will make the images look better. So, and then you can see some like example problems, like if you have the original input image here, and then we reconstruct from 1,000 log probabilities of this ImageNet classes, and then you can see when you're trying to reconstruct, it is coming very close to how the original image should look like. So this is coming from a bottleneck latent space, and then we use this above optimization function, and we then see that, okay, we form that similar dome structures in most of these. And there is some also, so the curve, right, which is very similar to the original image curve. Obviously there are a lot more details which are not very clear, because the this field itself, explainability, is a huge research field. People are still trying to identify how to visualize or explain CNNs, but still you can see a lot of details which easily you can relate with the original image. This is some more examples you can see when they were reconstructed from the latent space. So this is from the AlexNet. So as you can see, these are the bottleneck layers. That is after the last pooling layer, the first FC layer from AlexNet model. And you can see that when the reconstruction happens for images which are simpler in shapes, right? Like for example, this pear, which is just a circle. I mean, like obviously there are finer details like the curves, right, on the fruit. But if you look at the overall shape, it's just a oval shape, kind ellipse oval shape kind of a thing, which is very easily captured also. And also you can see even pairs which cause easily captured, because it's most likely just spheres, right? So it got captured. Whereas if you go to more complicated shapes like the seal over here or the car over here, although you capture the features, although you are able to reconstruct it more or less, but still, because of as the features get more complicated of the actual input image, reconstruction becomes a little bit harder. Even the seal, although it is trying to reconstruct, the details are going on. Same for the car, a little bit of haziness in the top, and the wheels are not exactly very clear. Whereas compared to the others, which are simpler, they can be easily reconstructed. So maybe just I'll just stay over here for 1 minute, and maybe if you have any questions or anything else, you can ask me right now. I'll just pause for 1 minute.
Hello, am I audible?
Yeah, yeah, you're audible.
Actually, we are studying that intermediate images, right? So these
Mhm.
are and these pictures are input images, right? Then how that's confuses me. How it is
Ye-
intermediate.
No, no, the cars are the input images,
Mm,
and from the
mm,
bottleneck layer, which is this particular layer, right, on the top I wrote, that will be our
okay.
bottleneck layer. So from there, this input image is
So
also sent to,
bottleneck means auto encoder kind of, right? Bottleneck that I didn't get.
no, it's not autoencoder. Autoencoder, not just an
Okay,
autoencoder,
that's
in any CNN model, you have
okay.
convolution layers, first few layers are
Mm,
convolution, and then you have final few fully connected layers, right?
yes, yes.
Right? In between that convolution and fully connected, there will be a layer, right? From where you're making that matrix into a vector and then sending that as an input to fully connected.
Okay.
That between layer where we are converting from that matrix representation of an image into a vector, and that vector will become as an input to the fully connected layer. That particular is called the bottleneck layer. So it's in
Before
any,
fully connected or
yes, before fully connected.
okay.
So it's there in any network. It's not necessary that is only in autoencoders. It can be in
CNNs.
anything.
Okay.
So what we do is we take from that Latin space and we try to see if we can if we can construct our original image.
Yes.
Yeah, yeah. Is it okay? Is it clear?
Yeah. Okay. So here we are reconstructing again to see that how intermediate. That's I'm not getting. Like reconstruction problem we are doing, or we are just interpreting the intermediate layers.
No, no. Here we are doing the reconstruction.
Okay.
So if you're able to reconstruct, inherently means that features are enough to tell, right? That it is basically those features are enough for us to explain what the model is looking at. You don't need extra other features. So inherently, a reconstruction problem can be also solve the visual explainability.
Okay. So okay, the first we input videos and second one is the reconstructed by our net model, right?
Right, right.
Make a slide. Okay. 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 Thank you. It's quite really impressive.
Okay.
Okay.
There's a question in the chat. Image update gradient ascent. Uh, I I think, are you talking about this particular algorithm?
Yeah,
Okay, so what exactly, uh, like the entire algorithm?
like how are we supposed to maximize the objective function? Like anything?
Okay, sure. So imagine like basically if you take initially it's all zeros, right? So and now if you get the final output, your final output from the CNN layer will have a logit, and then usually what you do, you calculate from a loss function because you have a ground truth value, and then you take that gradient and you send that gradient back. But instead over here we are saying that take the gradient only to be of this particular structure. One is where that particular class you want, so the gradient itself will be this coming from the final layer, and all the intermediate layers will use that gradient multiplied by the intermediate partial derivatives, and then you keep on back propagation. If that's how back propagation happens, right? We take the final gradient, we multiply the intermediate partial derivatives, and then we update our weights of that intermediate layer. So here, since we don't have any ground truth value here, what we do is we set that gradient from that last layer, which should come back, which should start the back propagation, that you set to be this, and then you keep, since you know already the partial derivatives, you multiply the gradients of the partial derivatives and this particular gradient, and then you update your intermediate weights. So you just do this for the image also. Basically, you go and do it for the final image x, because you know the partial derivatives with respect to x, and then you know the gradients of the final layer, and you multiply and you update the images in a certain direction. When I say update the images, I mean that basically do some pixel value increase, like you say, like you can see the images over here. Initially if it's all zero, it will all be white. Then I say, okay, maybe do some plus ones, or like plus 25, plus 40, some wherever there's intensity, right? You do some plus some values. So whichever plus value you do, it might be right, it might be wrong. If it is right, you'll get a good gradient. So and then it is okay. If it's wrong, then you get a high gradient and you try to go in the opposite direction of that gradient. So basically based on that gradient signals which you get, you keep on keeping certain pixels in this zero image, a certain high value and certain low value. Is that clear?
So when we say argmax, like what exactly are we doing there? Like the scores or something we calculate and then we take an argmax for that.
Sorry. So
Um,
okay.
yeah,
So
like
yeah, please go ahead. Sorry.
no, there's an argmax of I, SC, the score of the image minus I think lambda and then regularization. That particular formula I'm not understanding.
Okay. Maybe I think that was in the sir's lecture. Maybe
Yeah,
we can look at it after the slides, and maybe
it's
in the
okay.
end of the class, I'll open the lecture slide, and maybe you can look in that particular slide.
Sure.
So exact formula I also don't remember at the back of my mind. Maybe we'll figure out which slide it is, and maybe I'll explain it.
Okay.
There's a question in the chat. Can we apply for the so the logistic questions I would suggest please ask in the discussion forum. Like I'm not sure the exam registration deadlines and everything. So all the logistics related to the course you can put it in the discussion forum and they'll answer it better. And then we come to one of the popular methods, which is the class activation maps, also called CAMs. And so now that we have this particular CNN which is trained to say that this is a particular human object, like the class is human. So now people started wondering that the last convolution layer, if we attach another fully connected layer and some weights to it, can we identify based on these maps which we're getting can and this weighting which we're getting, can we identify which particular activations in this particular maps, given this combination, linear combination of that weight and that maps, is going and saying that this is a particular class, Australian Terrier or some other class. So the basic idea behind class activation maps is this itself. So you have your trained convolution neural network, and then we add this one layer which is marked in yellow, and we have these maps coming from the convolution layer. We do global average pooling, that is what this gap is, and you get these after global averaging pooling across each of these cam maps. Like if you see the color coding, the blue global averaging pooling corresponds to this node, the green one corresponds to this node, and once you get the global average pooling output, then you have certain weights, basically w1 to wn, which will decide what should be the combination of these activation maps, the linear combination which is shown down, and then you have your final output layer which is corresponding to each of the number of classes. So all we're trying to see is which particular combination of these activation maps, combining these activation maps, will actually finally contribute to which class the particular CNN is outputting. So very similar, a very simple technique, but very it actually give a very unique and improved accuracy, like explanation. So if you look at some of the cam maps, so you can see exactly where the CNN is looking, and the 0 points are the confidence of basically the predicted probability confidence. And if you can look at this, the dog, that's basically looking at the head. Similarly, for this particular dog, it's looking at the features value. For this dog, it's usually looking at the head and deciding. So wherever the intensities are high, it is saying what it is belonging to, what class. And this is a very good example if you look at the barbells. So it's very likely that it can directly say it can detect humans, but because there's so many objects over here, humans are there, barbells are there, then there is some other external objects also, like in this some other balls and all, but it is very clearly deciding what is a barbell. It's not just saying, I mean, some obviously misclassifications, like you can see, it is considering this particular ball also as a barbell because it is circular, but more or less it is identifying these as barbell because there's a rod connected with it. Similarly, there are two barbells at a particular distance, right? Usually that's what intuition hypothesis is, that barbell will have a rod connecting two circular things. So we can see that it's always two things which is connecting and saying it as a barbell. So we can always form more and more you can come up with more and more reasonings for why exactly it is looking at these. And but we can at least now understand on a very high level or a bit in depth also what exactly the CNNs are looking when it is classifying something. So in this case, if you look, it is saying 0.4 confidence only because although it is looking at the barbell, it actually got confused with the another's like this particular human body also as barbell. So it is still classifying as barbell, but not very confidently because of this other distractions. So these are some of the examples. So coming to some pros and cons of CAMS is like first pro is that it doesn't require entire back propagation of the trained neural network because we're not going back anywhere. We just need to train that few layers which we added, right? The global average pooling needs no training. It's that one layer which we add, which has the W1 to WN. We need that training itself. So that is one of the cons actually, which you can see in the third point. But pros is you don't need the back propagation of the entire neural network, only the retraining of that particular layer which we added. And like I explained, if it's a complicated computer vision task, it might not work really well. Like if it's multiple objects, multiple similar objects, and like does not, it takes what do you say, or some complicated detection task, segmentation task. It might be a little bit harder to use CAMs in those cases. And again, problem is when you're retraining, right, on that final layer. So the second you start retraining your already very accurate trained model, so there is a trade-off now happening because now the model also loses some accuracy because it's trying to come up with this weight values which will do the uh, what do you say, which will help us see what activation maps it is looking at. So there's always a trade-off between the how much you want to interpret and how much accuracy you want from that particular model. So these are some pros and cons. So yeah, any questions or anything on this camp? So basically, I wanted to explain these, and now I'll go to some code walkthroughs. So the code walkthroughs I had thought because from the last week session I stopped at how you develop a MLP, how you create a multi-layer perceptron, a very basic multi-layer perceptron I showed. I think I just showed one layer neural net, multi-layer one hidden layer multi-layer perceptron. Today I wanted to give us some more understanding since your assignment 4 is also completed. I wanted to give some understanding of what data augmentation techniques and how to implement that, and in general what functions you need to have in set before training any neural network. And then I'll show you a full-fledged MLP. And then if possible, if time permits, then I can also explain a little bit about how ResNet can be implemented in the code basically, like what all blocks do you usually go under ResNet. So before that, any questions in the CAM architecture or anything? Maybe I'll just pause for 1 minute. If you have any questions, you can ask. I think VP, I think maybe, like I said, what I was explaining about the exam is you can post it in the discussion forum. I'm not the correct person to tell if your dates for the examination registration is done or not. So any logistics related, you post it in the discussion forum of the course. The concerned person will actually answer your question more accurately. So
In hello,
yeah,
in
yeah,
CAM architecture, we the weights we assign at the ending part, or can you show the architecture that graph?
yeah,
Yeah, this one. So at the ending part, we introduce that map, activation maps, or
right,
in
right.
between also we can do.
Uh, in between, I don't think I've seen anyone doing because there's no point in doing it in between. You can try. I think people have done with multiple in between and then also a final. Because what we want at the end of the day is it should relate to something else. If you just do it in
Yes.
between, it's not relating to anything. You have to, if you create a layer over here in between. Firstly, it is not completing all its convolution, so the features might not be accurate itself. And if you just connect it from here to the last layer, it might lose out on important features which are coming after that particular layer. But if you want to take another route and you say, okay, why just stop at one particular layer? After every convolution, I'll put a global averaging and do. In theory, you can do that, but I don't see how it will help more. In fact, there'll be a lot of computational cost because you have to train again. Remember, whenever you're adding, you have to train the model. So the model might actually lose its accuracy also a little bit if you keep on retraining on so many layers. So uh, although I'm not saying you shouldn't, there are papers I've seen. I'm not exactly sure of those papers, but I've seen people try some other techniques like what you suggest, like why just stop at one? Like maybe some other techniques, some more layers you can add into.
Okay.
Okay, then if there are no further questions, I can we'll go to the code walk then. Yeah. So, sorry, there was a question. Does finding the mean of a cam have any use? What do you mean by finding the mean of a cam? Like, what does finding the mean? What do you mean by that?
Like if I get the median, I mean, it's one of the
No, sorry.
assignment questions that we did. So we were asked to find the median. So is there any use for that? I was wondering.
Median of a cam. What do you mean by median of a cam? I didn't get it. Like, is it the median of the weight values you mean?
Yeah, yeah, all the weight values. We just have to.
Okay, okay. I don't think so. I mean, is it a programming assignment problem?
This is a normal assignment problem. So I mean, is it like center of the? I mean, something like that. I was just wondering.
I really don't think so because think of it as like a linear combination of any vector values, right? So if you have any linear system of equations, what will the median of those parameters give you? Median or mean of those parameters? I don't think they actually say anything. Each of them individually says the priority of that particular map. In this case, like W1, if it's high, it means that the weight, like you have to prioritize the first activation map. But if you take a median of all these weights, I don't see that it contributes. It gives any information. I don't think so. I'm not sure. Maybe I'll also maybe look into that or reconfirm once. But according to my knowledge, I don't think it adds any information to it.
Sure.
It could give like most of the occurring weights, like if you wanted to see that median could be like help there, like
Yeah, yeah. But median
it
doesn't talk
help.
about occurrences, right? Mode talk
Mm.
about occurrences. Like mode
Could
is
be
the
midpoint, no? Like we arrange and then take a
right,
say
right.
mid
But
mid
how
of that point. Yeah.
that might not really help in our case, right?
Yes, yes, that's not making much sense.
Yeah.
Mm.
I think maybe like someone commented in the chat also. It could be just if it's a programming, I think it's very likely just to check your code. Like you have different weights, so you need one output as an answer. So for that, we usually use any statistic, median, mode, or anything.
Mm.
Uh, for the code, if it's like that, if it's an assignment problem related to code, it's usually that. Yeah. Okay. Let me just go to. So just a little bit, I'll talk about data augmentation. Very important part of any neural network, not just CNNs. Even I think nowadays, even in transformers or RNNs or whatever deep learning method you take. In fact, even for just machine learning also, data augmentation plays a very important role. In one line, data augmentation basically we try to diversify the data. So instantly we are improving the sample size, which is very important when you come to these machine learning, deep learning models. And again, it's not just some random improvement of samples, like we're not just replicating, we're not just copying the existing samples and making it double. It's always with some minor changes to our existing data set. Like the changes could be, since it in our course, which is images, you can think of it as like changing the intensity, changing contrast, or rotating, like flipping horizontally, or rotating just with some angle 90, 180, or some other angle. Or sometimes it's just random cropping, like you just randomly crop your entire image, or you just randomly there's something called as, I don't remember the name, but what it does is basically it makes some pixels as noise, like white noise. Basically, it increases the white noise based on how much value you give it to that. So there are so many different augmentations. So some are called strong augmentations, some are weak augmentations. Usually we use a standard weak operations when, because if the more stronger operations you do, the more harder it gets for the data to learn. So we need to, there's a trade-off. You can't just keep on doing all types of augmentations, then your CNN model will never learn the task. It's very hard. So people go for a standard, usually 3 to 4 augmentations, which is your random crop or random resize. There is a small difference. Maybe you can always Google and see. I'll leave that for you. There's a small difference between random size and random crop. And then people usually do for horizontal flipping. Basically, you horizontally flip. yeah, these are the standard three techniques which most of the people use. Normalization, which is very important. I think that is not exactly an augmentation technique, but that is since uh, PyTorch does normalization in that library of transforms, so people call it as augmentation, but it's not exactly augmentation. It's basically you're trying to bring everything into same scale, which is 0 to 1. So you do the normalization also. And also, like I explained in one of the earlier live sessions, always remember when you're normalizing, like you have some mean or sigma values, right? When you normalize, so that mean and sigma you get from your training data. So always use that mean and sigma when you get from your training data to normalize the test data. Never use the mean and sigma separately for both test and training data when you're normalizing, because in that case you're breaking the rule that you're not seeing the test data in, because basically if you're getting two different sigma and mean for train and test, it means that you're seeing your test, all the test data which you have with yourself, and you're creating a statistic which is against the rules of how you should train the machine learning or deep learning model. And I think apart from that, more or less these are the standard augmentations which most people use. Make sure it is also what your task specific also, like even if it's images, like if your task is, let's just say, a medical imaging, which is very important if people like if some people are interested in that field. When you're doing augmentations in medical images, be very careful. You can't do random horizontal flip. Like for example, MRI, CT scans, very, they have a lot of information in each of the direction. Horizontal flip doesn't work in that case. So that is actually one big problem in medical image field, is that there's lack of data. Augmentations can't be used like we use for other autonomous vehicles or anything, because the second you do some random augmentations like flipping, cropping, random flipping, random cropping, you change the data meaning itself. You change this image meaning itself. So there are some other techniques people use. I'm not very sure, but make sure your what your task is also, that if this augmentation is gonna alter your task, that is very important when you're deploying your models in real world. So yeah, that being said, let's first again, always like I said, very important is your libraries. So you have certain libraries which PyTorch gives you, and these libraries actually ease your way into doing different data augmentations and also loading the data set and transforming into data loader. So there are two different, slightly different things. Maybe I'll say these now again. Like I explained in the previous session also, there's a difference between data sets and data loader. So library data sets, what it does is, it's like you can imagine it to be a package where it understands what type of data set you're loading. Either are you loading directly from your root directory, or or you're loading from some other place. But all of them, when it loads, right, the data set, it loads in a certain format of where the particular root folder is and where each of the sample is present and what is the label of that. Once you create a data set in that particular format, I mean, like once you give an input to that data set, and the variable which you create the data set with, that you pass it through the data loader. What data loader does it, once you get the data set, the data loader then splits it into different batches. Like usually you have each batch of size 32, right? If you have like 1,000 samples, you divide the 1,000 samples into some X number of batches. Each batch will have 32 samples. So that division itself data loader does. And uh, and if you want to apply augmentation, data loader applies the augmentation. I'll show you how it applies. And also, if you want to do the random split, right, data sets does the random split. You can always Google how to do that. Basically, there's a function called as I think it's called random underscore split in PyTorch. You basically have to look into one two lines. I didn't actually include in this. I'll try to include that here and upload this collab. But yeah, you can always use this random underscore split from PyTorch and split the data set include using this data sets package, and then after that you send it to the data loader. So data loader doesn't do the random split, make sure of that. So data loader, all it does is split your entire data set, whatever data set you give it to, split it into batches, how many batches you want, and what are augmentations you want it to be done. And another important thing for data loader is when you split this batches, like number of batches, right, your entire sample, So based on your systems, sometimes it takes a lot of time because there's when you're training the neural network, data loader doesn't load all the batches on your GPU RAM, because then it will need a huge GPU RAM, which is not possible in real world. All we have is 32 GB, 16 GB at max. We don't have more than 32 GB commonly available GPUs. So what data loader does is it just loads one batch of that particular batch size only onto the GPU RAM when it is training the neural network model. Once it is done with that iteration, it just sends it back to the secondary storage and then loads the another batch. So this loading and downloading the sorry this uploading and downloading of these batches, right, it takes time. So there is a parameter in data loader called the number of workers. So sometimes if you're running on collab, and if you feel like, not just collab, like if you're running on any system and you feel like the model is training fast, the training of the model is happening in a faster time, but the loading and unloading of the data from the GPU, from the RAM to the secondary is taking time, you can always increase the number of workers in data loader. So you can always Google more about it. This is just some few techniques and tips which I learned over the years. So you can also use when you're implementing your codes or when you're implementing for other projects. Okay. So I hope it's clear the differences of what datasets does, what data loader does, and what else transforms augmentation and all. So coming to another library, which is again very important, called functional, which we usually import it as F. So functional is a library which has most of these what do you say operations, like you can call it operations like softmax, or what do you say, cross entropy, or any of these activation functions, ReLU or sigmoid, all of these mathematical functions, those are usually there in this library called functional. So you can just call f dot, like since I'm importing it as f, you can always say f dot sigmoid, f dot ReLU, or f dot softmax, and you'll basically get that. Apart from that, the torch is basically PyTorch. PIL is a pillow library which is used for visualizing images, loading and reading images or visualizing images. Matplotlib, like in every other previous live sessions I've said, it's used for visualizing data, any data, not just images. Okay. So coming to the first transformation. So usually you have two different transformations which we do on the data sets. We have your train transform, test transform. So when I mean transform is augmentation. So I use that. Usually people use transforms and augmentation interchangeably because PyTorch calls it transforms. So that's why people call it transforms. So in this transforms, if you look at the train transform, you first have a library package from Torch called Torch Vision. Then you say Torch Vision dot transform dot compose. So what these lines are saying is, I have multiple transformations to be done. Compose all of them into this one single variable called training underscore transforms. So whatever n number of augmentations you want to do, you can do all of them inside this compose function. You can mention all of those, and it will just compile all of those and send it into this variable training transforms. So different what are the different augmentations I'm doing? One, I'm doing resizing. Very important again, because at least like not for the datasets which you will be using in your assignments, but when you actually go for your jobs, right, you usually get images which are not of 224 or 512. You usually, because our phones or cameras in general capture if you go for like a good pixel camera, sorry, good resolution camera, you get of bigger size like 1024 2048 cross 2048. So in those cases you always need to resize to a certain smaller value, because like I said, the bigger size, more number of pixels, and now you want to collect a lot of samples, so the size of the dataset will become huge. So in order to reduce all of that, it's better to always reduce your size, because most of the times if it's 224 or 512, you can use and get better features from your for whatever task you want. You don't need such high resolutions unless it's a very sensitive task, but more or less 224 512 works for most of the tasks. So always resize. In this case I just resize to 32 because the data is very small. And then random crop. So basically from the entire image, you just randomly crop out 28 cross 28. So there are two cropping systems which are possible. So either you do center crop, it means that in that entire 32 cross 32 image, 0, comma 0 is the center point, right? And then keeping that 0, comma 0 fixed, you go 14 left, 14 right, 14 up, 14 down. So that is called a center crop. Whereas if you want to do random crop, you just randomly pick some patch of 28 cross 28. It is not from the center. A good exercise for you guys could be testing out how the accuracy affects for random crop and center crop. A very good exercise for you people to understand the importance of data augmentation. It'll be very you can clearly see. I mean, it doesn't work on all the data sets again. So maybe you can try it on the basic data sets which are available on PyTorch, and you can see the effect it shows. For some data sets, it's very sensitive when you do random crop and center crop. You can always experiment with that. Coming to next one, a random rotation. Again, like I said, if you want to rotate your particular image to 80 degree, some particular angle, you can use this random rotation. Sometimes people don't use random rotation, instead they just use horizontal flip, but you can always do random rotation. These other arguments I'm not explaining, but I'll share the collab file. You can always read the documentation of what each particular augmentation will do and each particular function is doing. You can read the documentation. Important thing is this two tensor. That is very important. And even if you don't have any augmentations in your if you don't want to do any augmentations for your data, always you have to convert to dot two tensor. What it says is, because images are not in tensor formats, images are usually, I think it's in bits format. Whenever you use PIL or any library, it's usually in bits format. So once you load using that bit format, and then you convert into a correct format which you want, you can either convert into a NumPy array, but PyTorch doesn't deal with NumPy arrays. You can convert NumPy arrays again to tensor, but instead of that, you can directly convert any bitmaps into tensor using this dot to tensor. So make sure that even if you don't have any augmentations, you always include this particular dot to tensor. So that is why we call this transforms. We don't call this augmentation, because we transform using this tensors, like we convert the data types. These are not augmentations, these are just transformations. So that's why people use transforms and augmentations interchangeably. Like I said, normalization very important. It will help you train the data faster. It will actually help a lot with the training process. Always normalize your data between 0 to 1. uh, Not just for images, usually a standard approach for any kinds of data. But if it's a sequential data, which we won't cover in this course, but in just for information, if it's sequential data, I wouldn't suggest using this type of normalization. There are other techniques which do for sequential data. Okay. And coming to the test transforms, so in there's a difference between usually what we use in test and training transforms. Like for example, we want the cropping to be always center cropping, because one thing about test transforms is we don't want any randomness in the test data happening, because we report our final accuracy with the test data. So when you're augmenting in the sense when you're transforming the test data, it should always be in such a way that the value you're getting, right, 99% accuracy, test accuracy. How many ever times I run that trained model on that test data, it should always give me 99% accuracy. I'll tell you how the difference happens. Now, for example, in this third line in the test transform, if you look at, sorry, if you look at this line, center crop, this center crop, if I replace the center crop with the random crop like I use for training, so now it is no longer a deterministic transformation, right? Every time I run this particular code, every time the test data which is getting generated, which is getting transformed, is a slightly different from its previous one, because we're using random crop, we're not using center crop. Now, because of that slight deviation, your accuracy won't be exactly the same, 99 point so and so and so. It will become 98, sometimes 97, sometimes more than the 99.4, it will become 99.9. So we don't have that deterministic accuracy. Even in your assignments or anything, make sure your testing augmentations don't have any randomness. It's always, if you look, all of them are deterministic. One is just converting tensor, one is just standard resize, no randomness. One is center crop, again no randomness. Again normalization, which is standard, no randomness. So make sure your test transforms doesn't have any randomness involved. Otherwise, your reproducibility will be a. I think there's a question. Do we need to call composite function if we are only doing two tensor runs? I don't think you need to call composite function. You can just Uh, wait. I think yeah, it's better if you call composite function. I'm also not very sure. You can directly do dot transfer, but I think it's always better if you use a compose function. No, sorry. My bad. You always need to use compose function. Even if you're using just two tensor, always use compose function. You can't just directly do that. I think it's if it since you're making these as a transformable what is it callable functions, because this will go into data loaders, and data loaders take input only composite callable functions. So even if you're doing just two tensor, always send it in compose. It's better that. And then this is just a simple MNIST data set. So PyTorch itself have some inbuilt data sets, like PyTorch has a lot of data sets: MNIST, SVNH, Fashion MNIST, Food, then ImageNet, then Celeb. So many. I'm like I'm just listing out the popular data sets. But yeah, so you can always access those data sets from this again library called datasets dot whatever the name you give. And for some of these data sets, I mean, like you can always look into the documentation, but for some of these data sets, they mention if there is a training and test split already there, then you can do like at a train true, train false. Then it uses that split. And over here, you give the transform. So, oh, sorry, my bad. So the transforms actually go in data sets. It doesn't go in data loader. Sorry, I misspoke in the beginning. So transforms, when you're doing augmentation, you should send it to the data sets step, not the data loader step. Data loader doesn't do transforms. It just does the splitting of the samples into batches. So the transforms are again done in data sets part. So similarly, you create your two data sets, train data set and test data set, and then after that you send this data set into data loaders. Like you can see, this data loader is the class we input will be the train data set, and we say how many batches, how many samples per batch, which is your batch size. The shuffle is true if it means that it will basically shuffle the entire data before it splits into batches. Always keep shuffle true for training. And like I explained in one of my previous sessions, why it is important to make your maybe like someone can answer actually to keep it more interactive. Maybe someone can explain in the chat, or maybe you can unmute and tell me why do you think we should shuffle? Why is it a good thing to shuffle your training data? And why do you think it is a good thing? If you shuffle, what is the benefit? If you don't shuffle, what is the disadvantage? Any guesses? You can just type it out.
No, it should not learn any sequence, like if those to break the sequence of input data.
True. It is what exactly has been suggested. So if we, I'll just explain one more line. What it does is like if you have two classes, if you have three classes, 0, 1, 2. If my initials 100 samples are from 0, 100 samples are from 1, and 100 samples are from 2. And if I train my CNN model, remember that all of this are happening iteratively, right? Like if I assume my batch size is just 10, after every 10 samples, I update my neural network using the gradient descent algorithm. And so if I have my first 100 samples belonging to only class 0, so the first 10 updates, because the batch size is 10, the first 10 updates will be only catering to what the class 0 should be like. And then suddenly the next 100 samples will be class 1. So the loss will be huge, and then the gradient will again try to go in some other direction, trying to cater only to that one, because the next 10 updates are only related to that class 1. So in this way, actually the model doesn't learn, because each time these next n number of updates are happening contain without looking at what the other classes are. It's a very bad way to do your gradient descent. So what people suggest always is shuffle. So the more you shuffle, the more randomly you give the data, the more gradient descent algorithm will actually approach to your local minimum. So there's some comments or it brings one. Like Moini Prasad said, it's kind of like a regularization. Also, you can, yeah, you can call it in that way. Basically, it randomizes. True. Like Ramesh also suggested, yes. Yeah. Then, so like I suggested, train loader will all you use data loader, and we give the input as train data set. You give your batch size, and you always shuffle. Test data again, you don't need to shuffle because you're not updating anything. If you want, also it doesn't affect if you shuffle if you don't shuffle test data, because there's no update happening. So these are just outputs of what you do from Colab Notebook. And this is just to check your data set. I mean, this is not related anything to PyTorch. This is not related anything to training your CNNs. This is just a good check always once you load any data set. It's always a good sanity check to see what the data set looks like, what samples look like. You'll understand what each of the data set, each of the image looks like, and is it a black and white image? How complex is the image? It's always better to understand your data very well before applying any model, because sometimes you don't need over complicated, like deeper or deeper CNNs. Maybe just two layer CNNs works. Like for MNES you don't need a ResNet 101, ResNet 18, which is just of 18 layers, or even forget ResNet also, even AlexNet, which is just of 4 5 layers, will do a very good job on MNES type of a data. So it's always a very good thing if you always visualize and see what your data set is. A very good thing is also to check your shape of your data set. The shape, what I mean by shape is this output which you see, right? 128 cross 1 comma 28 comma 28. So it's very important to check that also, because sometimes when you not when you're loading the pre-existing data sets, sometimes when you load your own data sets, it might happen that the channel dimension will come in the last, and then but whereas the PyTorch CNN module, which is there, the CNN module, it always takes input in such a way that the channel is in the second position. So it should the shape should always be, the first dimension will be the number of samples in that batch, which is 128. Then the second dimension should be the channels, third will be the height, fourth will be the width. This is what the CNN will take as an input. So make sure you always have that in the correct order. This is just another experiment which we do without doing any augmentation, just to see how augmentation affects. You can always run this codes and check how augmentation actually. So if you see one augmentation technique, like the difference, what happens is the 8 number, if you're seeing 8 over here is like this, whereas it is rotated, whereas actually 8s are like this. Similarly, 7, if you see, this is a bold 7, whereas if you see, it's a little bit, I don't know if it's very visible, but it's a little bit blurry over here in this 7. Similarly, for 6 also, a little bit angle rotation is there. So you can always look into this particular collab file once I upload it. So you can not just this, you can always visualize more and see how data augmentation does. Yeah, so these are just another some helper functions for the same data loading. So you can always look. So this is like the whole function which will call the previous values, like which will inculcate all the previous steps which I said. You can all create in this particular function called get data loader mnest. You can combine that and create this one big function. Yeah, so this step is what I was talking about if you want to do random subset split, right? So if I said that if you have your training data and test data already available, but now you want to create a small validation step also, or sometimes you don't have the test data, now you just have your whole data, you want to create a test and train split, right? So for those cases you can use something, a logic like this. This is not the only way to do it, like this function subset random sampler. This is not the only way to do it. There are other ways in PyTorch which you can do, which you might find it simpler. This is one such way to do. So you find out the total number of samples, which is 60,000, and then you randomly pick all the indices. So this num, what it stores is, stores all the indices of in that 60. Sorry, uh, num is basically how much number of validation samples you want, and then we indices will be from 0 to how much ever 60,000 minus the number of validation you want will be for a train, and the remaining will be for a validation indices. And once you get the indices, you send them to the subset random sample, which will take care of all the indices which you want them to be as train and valid. And then you use this sampler in the data loader call. Basically, when you're calling the data loader, you send this sampler. So as the name suggests, what the sampler does is it picks only those samples which are belonging into your train. It doesn't touch the samples which are going into validation. So it's very intuitive. The name suggests the same thing. So randomly it picks from the entire samples data set. It picks a subset which is your train. In that subset also, it randomly picks some samples and creates your batches. So this is one way to do the split, but there are other ways which you can always see. And then you have these are some helper functions. So these are some functions which you can use to either do reproduce. Maybe I'll explain one by one. So why is setting all the seeds very important? So reproducibility is a very big, as you can see, entire deep learning concepts and all. A lot of randomness happens. Like your initialization of weights, it's a random. You pick from a random probability distribution, and your data set augmentations is again very random, and there's so many randomness happening. So one important thing in research community is usually the reproducibility. Like if I submit my research paper, not just research, if I develop a project, I want it to perform it the same way as it is performing on my system at my particular conditions. It should reproduce and produce perform the same way in any other laptop in the world. So because of that, it's always very important to set all the seeds. All the seeds. What I mean by that, seed term comes from this probability distribution sampling. So when you sample, you can pick randomly out of this 0 to 100. If I want to sample 10, I can pick a random 10 numbers from the 0 to 100. So seed, basically they say if I set seed as 0, it means every time I pick randomly, it will pick only those indices which are related to seed 0. Like for example, if I pick 5 numbers from 0 to 10, it is like 2, 7, 9, 8. This is corresponding to seed 0. Then if I do 10 times, if I run this function using seed 0, it will always pick 2, 7, 9. The second I do seed 1, it will go to some other combination. But if I don't mention any seed, then every time I run this function, it will pick some random combination. So in a very simple way, seed works this way. Now you can think that setting seeds constant throughout your training process, it will fix all the randomness wherever you sample it. It will fix all those things to one particular deterministic way. So your initialization will be deterministic. Deterministic as in it follows a standard randomness, and then your augmentation will also do the same thing, and all the other random processes. So that's what these two functions are. So first one is for any standard torch tensors and NumPy tensors. Then the second one is for CUDA deterministic thing way. So CUDA and CUDNN is basically two libraries which are very helpful to do parallel processing. And PyTorch actually uses these two to communicate with your GPUs in either your collab or your local machines have your GPUs, and it makes sure that the GPUs are activated and the processing, the training and everything whichever is happening, it's happening with the parallel processing and not sequential. You don't need to understand or go in depth of how it is happening. I mean, like it's always if you're interested, you can always do that. If you have any questions, also we can discuss some other time. But on the high level, just to understand, all it does is it communicates with your GPU to make your entire training process to be parallel and speed up your process. That's it. And then you have a function to compute accuracy. I don't think this needs to be explained. So it is a standard way. You get your you get your logits from your trained model, which is this. Sorry, you get your logits from the trained model, and then from the logits you find out whichever is the maximum, and that will be a predicted label. And from there you have your ground truth, and then you find out if that ground truth is matching with your target, and you find out for how many of all the samples in your test set is this equal, and you sum those up and you find your final accuracy value by multiplying with 100. This is a standard function. This has nothing to do with deep learning. Coming to training itself, so maybe before training I'll just explain the how to create the model. So yeah, this is a very simple multi-layer perceptron, but I'll just cover this once again since you also have to do assignments for CNNs. Concepts are similar how you create your CNNs or any model. Your template will be same. It's just what layer you're adding changes. So whatever I'm explaining here, if you understood the template of what is happening here, you can easily understand when to how to replace the multi-layer perceptron with a CNN model. So maybe I'll just explain. So always whatever class you create, right? You call, like in this case, I call it the sorry, one second. Okay, sorry for that. Yeah. So in this case, I call this class multi-layer perceptron. You can just call it anything. Whatever class you call, you always need to inherit this particular library called torch.nn.module. So this is important because this particular inheritance tells the PyTorch that this is where you're creating your network architecture. And this library which you're seeing, right, this actually helps. This first of all contains all your implementations of your linear layers, convolution layers, pooling layers, whatever other layers which are possible. Module library contains them. And not just contains them, it basically creates a computational graph also for them when you're calling them. And so all those things which you don't have to write from scratch, everything will be taken care of this torch.nn.module. So it's very important that whenever you create your network, any network, MLP, CNN, RNN, it's always important that you inherit this particular library. And the first function should be your init function, where you like whatever arguments you want to give. These are not these are not fixed. You can always give features, classes, or any number of arguments. And after, in this init function, the first thing you have to do is call the super class of it, the super dot underscore underscore init underscore underscore the brackets. So this line basically says ki you inherit all the important uh, global variables from your from your parent class, which is your torch.nn.module. So I won't explain much in detail. It's related to the OOPS concept. You can always go back to it, standard OOPS concept of inheritance and everything. It's basically that. So once important thing is you have to inherit the class and call the super function in the init function. And then after that, here comes the next important step where you create your network. So here you first give a template of what all the layers should be, and then in the forward you actually send your input and get your output value. So I'll just explain the first way. First, I'm creating a template of my network. What is my template? It should always be a not always, this is one way to create a template using nn.sequential. People sometimes don't use this. Instead, they use each of these layers, they give a separate variable for them. You do that if you want to get outputs from every layer in between. So if you want after this first flattened linear ReLU, if you want the output after this ReLU, you can't use sequential, because then if you use sequential will take the input and directly give output from the last layer which is there in the sequential. If you want outputs from intermediate layers, you create variable names for each of these layers, and then in the forward you basically manually send that input to that next layer, and that output of that next layer will become input to another layer, and whichever in between outputs you want, you can return them like I return logits. I hope this difference is clear. So I'll just say it again once more. There are two ways to create your network. Either use a torch.nn.sequential. What this nn.sequential does is it assumes that all of the layers which you mentioned comes in the same like what is the same way, like flatten, linear, ReLU, and it doesn't allow for output to come from any intermediate way. If you give an input to the sequential, your output will come directly from your last layer. But in another way to create your network where you want your output from intermediate layers to come out is you create names, self dot variable names for each of these layers, and in the forward function you manually send the data. Like for example, x is going to my network, right? Over there you'll go x to my linear layer 1, and you get some output, and that output will go to some self dot linear layer 2, and you get some output, and then output will go so and so, so and so and so. In that way, you can return how many ever intermediate outputs you want using this like I return the logits, right? You can return how many ever intermediate outputs. So these are two ways. Even for CNN, MLP, everything, this is a standard approach. So here, if you want CNNs, you can easily do this torch.nn.sequential, and the first is the flatten layer, and then flatten here. Maybe someone can say, why did I first use flatten? Like, why am I using flatten over here? Maybe any guesses? You can just type it out, or you can also unmute and say. Oh, correct. Yeah, like
Yeah. So because you are using a linear layer, which expects, like a single set, like 1D features,
true,
and your input is, like a MNIST maker, so you need to flatten it.
true, correct, exactly. So, well said. The answer is the same thing. You basically, since input is a matrix, your linear layer takes input as a vector, so you always flatten it out. Yeah, so since it's an MLP, you flatten it out. If you're using CNNs, you don't have to flatten out. So, and then you create your linear layer, and then you have your activation function. Then you use your drop. This is just a regularization. Depends on which regularization. Sometimes you can use batch normalization. You can use dropout. You can use both of them. Maybe a quick question. If I want to use batch normalization, uh, do I put the batch normalization after the ReLU or before the ReLU? Maybe you can just type it out. I'll just repeat the question. If I want to use batch normalization regularization, do I mention that after the torch.nn.relu line, or do I do it before the torch.nn.relu? Correct. Like Mohini answered, no, it does matter. It should be before. After actually takes away the normalization concept itself. So, for example, if you do after activation, because activation kinds of squishes away your data from your actually how it is appearing. So, input, if you have an input in a particular distribution, if you assume a Gaussian distribution, after doing linear, it will still follow that, but in a shifted way. But if you do activation, that Gaussianness will go away because you're then cutting off all these negative values to zero and then a linear straight line. So it's always suggested that before the activation function, it is important to do batch normalization. Again, it's an experiment which you can always try and check it out how it is affecting. And also one other thing. So another question could be: do batch normalization and dropout, can they happen both at the same time, or do we pick only one? Or like, can we do both batch normalization and dropout at the same time, or do we have to pick one? What do you think? Any guesses? They are independent, so they are completely independent, and you can always do. But this is a very recent research also. It's still not very confirmed. So people up till now, up till recent years, they have been using both batch normalization and dropout together. But people recently have, in some few research papers I've read, people have seen that if you use dropout with batch normalization, the performance is actually affecting. Instead, just batch normalization should be more than enough. You can completely eliminate the concept of dropout itself. But again, this is not a concluded proof that it can be. It is like this for all the tasks available. Your best option is try both and see. But always, you can just not use dropout. You can just use batch normalization, which works perfectly well. So, yeah. So we have your first hidden layer, then you have your second hidden layer, and then finally your output layer, which is your output will be a number of classes. And then you create another function called your forward function. Very important function. The name should be forward itself because that's what the torch.nn.module takes input. It should always be the name forward. In that forward, you say what is your input. You can give arguments, how many arguments you want, and then you send it to that particular network if it's sequential, otherwise to each of that network, like I said, if you're creating in another way your network, and then you return whatever your output should be. In this case, I'm just returning my logits. Now this is a template you can always use for CNNs also in a very similar way. You just have to you have to make sure that what you're replacing in this template, you have to see which layers are corresponding to CNN architecture, which layers are corresponding to fully connected layer architecture, and then easily you can easily understand how to create a network. So, and then I'll maybe touch upon a little bit about the training loop, which I missed in the top. So once I create my model, all that is left is for the training of that model. And so here you can see you have two things. We have your epochs, and in each epoch you will have your number of batches. And so in this second inner loop, we always first pick up that batch, and that is coming from your loader, data loader, which is my train loader. And then so you can always ask why in this particular way we are writing like for batch ID, comma, feature targets, and enumerate. I would suggest look into what the train loader actually gives output as a data structure. So train loader is a very important data structure which you have to look into, because I think without that you won't not like you'll obviously use train loader in any function. So train loader usually has certain structure where it gives your ID of the batch, it gives your features, what are their features in the sense like the images, and targets, which is your ground truth. So it always stores in these three, and exactly how it is stored, it's beyond the scope of this live session at least. But I would suggest a very good thing: always read upon the data structure of what the train loader is doing. So, but to call that particular train loader's different data values, you do use enumerate, and you get the outputs as these. And for each of these particular batch, image, and targets, you first send them to this what is a CUDA device. So device is basically your GPU. This is important because when you're doing your training, right, you want all your model, image inputs, image labels, everything should be on a common processing unit. It should either be on the CPU, which is by default, it goes there. If you have a GPU, you always need to send all of these important things to your GPU, and that is how you do with this dot two. That is basically sending it to your GPU. So there is, I think there's no reasoning, but it's a standard protocol. We want all of them to be on the same platform. Otherwise, PyTorch doesn't work. And once you do that, you always send your features, which is your input, uh, which is your images as the input to your model, which I just created in the bottom right. So I just send that as the input, and then like if you saw in that model, the output was coming directly from logits, right? So I get my output as logits, and now torch.nn.functional, which I can always use f over here, but just to show you, I use this full statement torch.nn.functional. I can use this dot cross entropy, and then I use these two logits and targets. So one important thing is the targets here at least are in not in a one hot encoded shape. Like it comes in like 0, 1, 2, 3, 4, 5, 6. In that particular trend, it happens. So if you ideally we want it to be in one hot encoder, but here we don't use that. But don't worry about it, cross entropy takes care of it. But if in any case in future assignments or in any other use cases, if for some reason you don't have targets as 0, 1, 2, 3, 4 to 10, but you have one hot encoder, you can always use think cross entropy with sorry, I think it is called cross entropy with binary encoded, or cross entropy with one hot encoded. Some option like that is there, function like that. I'm sorry, I don't know the entire name, but there is a function for you to use that. So if you have targets in your normal 0, 1, 2, 3, 4, 5, you can just use cross entropy. And for some reason you don't have the targets like that, you have it in one hot encoded, there is a function available for even that. So do check out that, and you can use any of it corresponding to what type of labels you have. After that, always important thing is you have your optimizer, right? You make sure your optimizer gradients are first set to 0. Very important, because if you don't set the gradients to be 0, you'll have some way wrong, you'll have gradients left over from the previous state, from the previous update, and that will interfere with this new gradients which you'll be calculating. So always make sure that your gradients are first zeroed out before you update in this particular batch. So you first zero gradient, and then you do loss dot backwards. So loss dot backwards, what it does is basically calculates your loss, and it also calculates your I think gradient at this step. It calculates the loss of that gradient and the backward sorry loss of it calculates the loss and the gradient of that loss. And dot step is basically where you're updating all your parameters throughout your model in that back propagation fashion. So entire the mathematical equations which you saw in your theory in week 4 about how backpropagation happens, gradient calculation happens, all of those is just these three lines. Very they nicely compositioned everything. They compiled everything into these very good libraries. All of the big calculations you don't have to worry about. All you need to remember is these three important steps to train your entire neural network. Zero your gradients out using this first line, optimizer dot zero grade. Loss dot backwards, calculate the loss value and the gradient of that loss. Optimize dot step, update all the parameters of your model. And these are just printing statements. Like what is the loss value after each batch, each epoch. I think you can just look into this as standard print statements. Another important thing is model.eval. So there are two modes for any model you create, any architecture you create. One is model.eval, one is model.train. Maybe someone can tell me why people use model.eval, like what benefit does it give? Maybe you can type it out, or maybe you can guess what model.eval is doing. Okay. Maybe I'll explain it such. So model.eval basically, if you're using dropout, right? So best example is with dropout itself. So when you're using dropout, do you have certain layers, neurons in the hidden layer which are not active? That's what dropout does. Dropout basically says that you basically drop out connections in some hidden layer nodes. So when you're doing model.eval, it says that no such randomness of dropping out of the architecture should happen. It should stay the same. So that is where you say that the final model is what model.eval does. It freezes your model. There's no update that can happen in your model. No, this dropout type techniques can happen. So if you want to freeze your model, model.eval does that. So that's why we use before, so finding out what is my training accuracy or test, so what is my accuracy inference, right? What is my training or test accuracy, train loss, accurate test loss, validation loss? You always need to set your model to dot eval phase. So then it freezes away all the parameters which can be random dropout connections or some other parameters. Always very important, use model.eval when you're finding out your accuracy values or loss values, basically when you're inferring. Otherwise, your values might not be like dropout. Again, another experiment which you can try, dropout actually changes your values. So if you have dropout and do 10 times, if you infer on using dropout, right, active dropout, your accuracy changes every time because dropout randomly drops connections. So your accuracy changes with that connections which are dropping. That's why model.eval is very, especially very important if you use dropout. There's like a comment in the chat sets training to false values. Exactly, like Ramesh has suggested in the chat, it sets basically your training to false. You can either use, I think there's some other function called model set training, but you can always use model.eval, which is very simple also. Model.eval take care of everything. So yeah, I think this is the training loop, and then you eval, and then these are just basically whatever is returning, list values and all. And yeah, I think more or less. So these are the important functions in this which I wanted to talk about. This is just an experiment of how the model accuracy changes with and without dropout or patch normalization. I'll upload the code, collab notebook. Everything remains the same, which I explained. It's just that other what I didn't explain are mostly plotting, which plots the values, which I explained in previous live sessions how to plot. So if you have any questions, you can always post it in the forum and I'll explain, or we can discuss in the next live session after you look into the code. So yeah. So this is how you create a basic MLP neural network using different data augmentations possible. Using data sets, data loader, you create your training loop and you create your model. You can how to create your model. You create a model either using the sequential part, or you can create other like you can call each module separately, each layer separately, and then you can use the forward function to send the input output for each of these layers. After that, if are there any questions, maybe I'll just pause for a minute or two because there's different code. I'll just keep it over here. Yeah, maybe I'll just pause for a minute or two, and if you have any questions, you can ask me. After this, I'll just quickly explain about ResNet once, and usually how ResNet type of architectures, people make big architectures, right? How such big architectures are made. Maybe I'll just explain that quickly, and then we can end the session. So, any question for this? Okay. Let me just go to the ResNet then. Yeah. So again, initially we do all this is a different data set called CIFAR 10 data set, very popular data set. There are two versions. I think if you are in this computer fusion field, you'll definitely be at least using this once in your entire career. CIFAR 10, CIFAR 100, ImageNet, very standard computer vision data sets, very helpful to see if your new model or if your model in general what you're creating is it even working. So people usually ask, if you come up with a new model, show us what is that model's accuracy on these data sets, because all the other models in the world they also compare. So these are like we call these the benchmark data sets. So it's very important to have an idea of what these data sets are. I think it'll be a good exercise for you to actually brush up on some details, like how many, what are the classes in general, what do these data sets even have in them. Like most of them, even Coco data sets, very famous. So just have an idea about what these data sets even mean. Yeah, coming to our particular ResNet. So again, initially we have some transformations. We have some train transforms, which is your cropping, resizing, and then we have your test transforms, and then you create your data loaders. Like this is a function which creates the data loaders, and you get your output, which will be a train loader, validation loader, and test loader. Now comes the important part of creating your big module like ResNet. So before that, I think ResNet, I explained, like it's a very important architecture which comes up with the concept called as residual connections, which is basically it takes the input from one of the previous layer and adds it to your next layer's output. So why is that important? Is basically when you're back propagating, sometimes if the layers are large, like if they're like 20, 30, 40 layers of convolution, and the gradient is actually small, and when you keep on back propagating that gradient, it always gets multiplied by even smaller numbers. And at one point, I think somewhere in between, like probably after 10, somewhere in between at the 10th layer or something, the gradient becomes zero, and all the layers before like the first 10 layers will not get any gradient signal coming from your last layer, because the gradient value becomes so small. To avoid this, this is called gradient vanishing, basically. The way, like the name suggests, basically the gradient becomes zero and no signal is coming. So to avoid this, people do these connections, like somewhere from the starting layers you connect to somewhere in between, so that now the gradient will take that branch and go to the starting layer. So now the starting layers also get some gradient signals. So this is why ResNet actually works. Many variations are there nowadays. ResNet, not just the number of layers, number of based on number of layers, there is like it's ResNet 34, 50, 101. I think these 150. These are the standard ResNet. And apart from that, there is ResNet X, which does the different kinds of concatenation, multiple variations. You can always look into those. And apart from ResNet itself, there are like something called as DenseNet, InceptionNet, so many architectures. But it's always a very good thing to remember these architectures and at least have an idea of what these architectures are like, because in any interview, if you ever go for an interview question, or in general if you're working in any industry, you'll always need to use these models first to see how it is performing on your data sets before creating your own model. If these models are doing the job very well, I don't think you have to create your own model. But if it's not, then you can see that what not to try so that you can create your own model. Yeah, that being said, so it's a very big architecture, 34 layers. I won't explain all the 34 layers. I'll upload the code. I'll just explain in general how you create, like what are these con 3 by 3 is doing, con 1 by 1. So con 3 by 3, it's a function which you keep on calling because ResNet, like I said, it has so many blocks, 34 layers, right? So they always come in blocks. It comes in block 1, block 2, block 3, and each of the block will have certain convolution layers in it. So people basically create functions for each of these block and they just keep on calling those blocks. So this is the same thing. Con 3 by 3 is, they're calling this convolution 2D with their what input output features you want and everything. Con 1 by 1 is also very important. So con 1 by 1, it is important. It's actually more important in another network called InceptionNet. So what 1 by 1 does is it projects your input image. Like for example, my input is 28, 28, 3. Now I want to increase the channels from 3 to 256 without actually doing convolution. So in that case, I will use 1 cross 1. So if I use 1 cross 1 convolution, I don't do any convolution, but I'm increasing along the channel dimension. I'm increasing a lot of channels. Maybe someone can guess or someone can tell me why increasing of channels is important in convolution. Why do you think that is helpful? Like, why do we use 1 cross 1 to increase the channels?
Yeah. So one cross one, I guess you can increase the number of features for the feature maps for the next layer, or I guess reduce it as well with the same
But why
convolution.
why is it important to increase the feature maps?
I think it gives you more opportunity for the model to capture different aspects of the input data.
True, true,
Maybe.
true. So I think one intuitive understanding I can give you people is in the initial starting classes, starting weeks, you learned about different filters, Sobel filters, uh, other etc filters which capture edges, which captures curves, which capture blobs and everything, right? Those are all man-made filters with domain experts. They follow a certain algorithm, and you get. So CNN, what is doing when you create these feature maps a lot, right? You can assume each of these feature maps in that entire list of feature maps will capture those somewhere along some layer in, if in the 256 channel dimension, it will have these edges being captured, blobs being captured, all of these. But the best part is you don't manually have to give any algorithm. You just give the random weights and you give this training process, and it will capture. So that's the best intuitive way of understanding how why even CNNs work, is because the feature maps capture the same things what we were trying to do in the initial traditional computer vision tasks, where we had a certain algorithm to capture a certain particular feature. So, but now since we have so many feature maps combined all together, we capture more and more complex features, like edges, two edges combined make curve, curves combined make more complex shapes, shapes. Then not just shapes and like edges, like colors combined make different objects look differently, and then there is occlusions. So many things happening, which we can't actually have a rule for everything, right? So all of these we just depend on these feature maps to do this. So in those cases, it's actually very helpful to do 1 cross 1 when you want to increase the feature maps computationally without efficient, because we don't do any convolution operation. Yeah. So now I create one basic block, which is basically in used like multiple times in the ResNet like blocks. I think there are different ResNets have different. I think ResNet 34 has 2 or 3 blocks. I'm not sure, but yeah, you can always look into the detailed architecture reading the paper. The basic block again contains this. You have two convolution layers, each convolution layer followed by batch layers, batch normalization and ReLU, and then we see how much we want to downsample. So if you have a downsample, you basically reduce the input size to whatever size you want. If you don't want, then don't downsample. Why is downsample important? Again, that's entirely ResNet architecture, which is beyond the scope of this. But just think of downsample as one operation like patch normalization or some pooling operation, which basically downsamples your input size. And this concatenation which is happening, right? Output is plus equals to identity, which is your this after downsample. This is where we do residual connection, is like I said concatenation which is happening, which is where most of your ResNet block happens. So inherently what is happening in this block is you get an input to the block, you do your two convolutions, and the output of that is added to your input, basically is added to this downsampled identity basically. And now finally you get one more output from your block, which will go to input as a next block. So this concatenation helps in that gradient vanishing problem. So maybe I'll just pause for one more minute, quick minute, and maybe you can see if like any small questions or anything. I know I went through ResNet a bit fast, but you can always read upon the actual architecture and we can always discuss more, because we don't touch on this exactly in this course like each architecture, because it'll take a lot of time. But you can always look up the architecture with blogs and everything. Okay. Similarly, we have another bottleneck layer which is very important in ResNet. So what I wanted to do with this is like see how simple it is we are creating. Like all of these, like if you look at the MLP which I created, right? MLP also follow the same structure. You create a class, import your module, and the first lines were init function and the super which you're calling the in parent class. These are standard even in MLP. And then these are obviously there are some differences that is because of ResNet, but you see the template. All of them follow the same thing. They don't use sequential because they want output from each layer. So this is the other way of creating a network where you create for each particular layer, you create a variable, and in that forward, you take your input, you send it to that layer, you get the output, you again send it to the next layer, and this way you return. So the template remains the same, whatever the architecture, however big your architecture is, it's always the same. It's just that bigger and bigger models have a lot of more functions, and you need a more understanding. Like this is one class, bottleneck is another class, which again follows the same template like I created for MLP. And then finally, ResNet is your class, which will use both the bottleneck and uh, basic block classes, and then creates a final ResNet. So it does look a bit complicated if you just look at this, but think of it as always following the same template of inheriting from the module parent class, then creating a architectural template, which is either using sequential or each layer, and it should always have a forward function, which will take input and you either you keep on sending it to the next layer. You can create any architecture if you understood this particular type of a template making. Yeah. So yeah, I think this is it for this today's class. So if you have any questions, you can stay or you can leave. Uh, Thank you all for attending the class. I'll be happy to take any questions.
Okay. Thanks for the session.
Yeah, thank you.